Now, we're going to be naming inorganic acids and bases, but before I talk about inorganic acids and bases, what makes an acid organic or inorganic?
Is it the sorry, I forgot. I didn't know.
Jared, what makes an acid organic or inorganic?
I know organic substances have to have a carbon and an oxygen, so I'm guessing a organic acid would have a carbon and an oxygen as well as hydrogen.
Good, quite warm there. The exact definition is that an organic acid has one specific group that we always pick up, and it's this group right here. You would have seen it written before. Maybe in year 11, you would have seen that acetic acid was sometimes written like this, and you may have wondered why on earth they've separated the carbons, the oxygens, and the hydrogens, and why they've done it so oddly. The reason is, it's to show you what the structure of that compound would be. Does everyone see? CH3 is then bound to a C, and that's bound to an O and an OH. And that tells you exactly what the structure of acetic acid is. Now, the actual functional group that makes this substance acidic is this. This is what we call our carboxylic acid functional group. Carboxylic acid functional group. In Module 7, you'll learn to master how to name these. For now, you just need to recognize when something is organic or inorganic as an acid. Okay, so if you see a COOH group, it is organic. Does that make sense? Now, we've mentioned that an acid releases hydrogen ions in aqueous solution, and I want to stress this a lot. These hydrogen ions do not ever come off, right? Unless it's some other reaction. They do not come off as an acid. They never get released as an ion in solution. It is only this hydrogen at the end that will be released and ionized into solution. Okay, and that is why it's the COOH group that makes an organic compound acidic. Does that make sense to everyone? Good. What's another name for this acid here? So you see ethanoic acid here. What's another name for it?
Acetic.
Good. And what's the household name for it?
Vinegar.
Good. What about this acid here? I'm not going to tell you its name just yet, but how many hydrogen ions would it release in solution? Riyasat, what's your answer?
3?
Yeah, do you see there's 3 carboxylic acid functional groups? And I told you none of the other hydrogens will come off in solution. Only this, this, and this. This is what we call a triprotic acid. Protic because, well, what is a proton? Proton is just a hydrogen ion, right? So a triprotic acid is an acid that releases 3 hydrogen ions per molecule of acid. This acid is formerly known as 2-hydroxypropane 1,2,3 tricarboxylic acid, or the layperson name you would know is citric acid. Okay, so again, you will not need to know how to name these acids at all, but it's good to know how many hydrogen ions they will release. And citric acid comes up a lot in your exam questions. So it's good to know it's triprotic in nature. I would remember it just as H3X. Okay, good. All right, let's move on. So with naming acids, I'm not going to bore you with this spiel. My tip for you would be, you should eventually get so comfortable with acids and bases, you don't have to apply any rules for naming it. You just see it and you remember what it's called. Okay, so I never use these steps in my head. I just look at it and you should know what it's called. So I'm going to give you all acids and you're going to tell me how to name them. So Gerald, we'll start with you. How would we name, I'll give you an easier one first. What would you call this acid? I'll help you out here. Is it a polyatomic acid or is it a binary acid?
It's binary.
Okay,
But
so
yeah.
whenever you're stuck, you need to link it or apply a thought experiment to what you already know. Now, I'm sure you know what this acid is. What do you call this acid?
Yeah, hydrochloric acid.
Good. Now, apply the exact same principles. What are you going to start this acid with?
Hydro.
Good, right? Now you noticed it was called chloric acid. The chlor represents the Cl,
Yeah.
but it always ends in ic acid. What element is this?
ID.
Good. So what are you going to add in front of the ic?
Hydroiodic.
Good. Iodic acid, right?
Iodic.
So this compound, you shouldn't have spaces like this, but just to show you the name, but it's called hydroiodic acid, and they should all be together. Hydroiodic and then space acid. Good. So that's how you name any binary acid. It's hydro and then ic acid. Okay. So this is hydroiodic acid. Risa, what about this?
Hydrofluoric
Very good.
acid.
Good. I'm not even going to write that, so that was good. Next one. Gerald?
Nitric acid.
Good. Risa, what about this one?
Nitrous acid.
Very good. Now, what principle did you apply? What is this ion called, Gerald?
It's nitrate ion.
Good. So it's an 8, right? It ended in 8. So this is what we call a polyatomic acid. And for a polyatomic acid, the only thing you need to remember is if it's an 8 ion, it becomes an ic acid. So nitrate becomes nitric acid. And nitrite becomes nitrous acid. Very good. So again, I'll give you 2 more. Risa, what would you call this? And yeah.
Phosphoric acid.
Sorry, what did you say?
Phosphoric acid.
Very good. Phosphoric acid. Good. And final one, you get an easier one, Gerald. What is this?
Carbonic acid.
Good. And I'll give you one more. Reset. What is this?
Hydrobromic acid.
Good, right? So you now know how to name acids and bases. Like I said, I don't remember any of this. I have to think to actually derive this. You should just look at the acid and know what it's called. And that just comes from practice and doing more and more questions. So you've already got that down pat for most of them. Here's a flowchart, but we'll skip all of that. You can do these questions in your own time. Next question I'd like you to do is, where's our question? There you go. I'd like you to do this question. So Gerald, what was a net ionic equation for both these reactions?
For the first one is H plus OH minus gives you H2O.
Good. And what about the second one?
The second one, it's 2H plus 2OH minus gives you 2H2O.
Very good. But if there's 2, 2, and 2, what can we do?
We can simplify it.
Good. So what are the net ionic equations? They're the exact same. Do you agree?
Yeah.
So if the net ionic equation is the exact same, is there any conclusion we can make from this? All neutralizations, yes, the first one is all neutralizations have the same net ionic equation. Very good. And Risa, what about the enthalpy change? If it's the same net bonds that are broken and reformed for every reaction, what can you infer about the enthalpy change?
The enthalpy change is the same for all.
Good. Do we know what it is, endo or exothermic? Gerald, if you had to guess, what would you say?
Most likely exo.
Good, because it's synthesis, right? And I want you to remember this, it's highly exothermic. In fact, it's one of the most exothermic reactions in chemistry. So it releases 57 kilojoules of energy per mole of water that's formed. Okay? So the enthalpy is extremely high for an acid-base reaction. And we'll come back to this. It's an important characteristic of neutralization itself. Good. Happy to move on? All right, let's come back up to some content. We'll talk about indicators. Now, what did you learn about indicators? We'll start with the definition. So, Reset, define an indicator for me.
I'm not sure for the definition of an indicator really.
Tell me what it does when you add it to an acid or base. What will it do?
It changes color based off of the pH of
Very
that.
good. That's perfectly what the description of an indicator is, right? That's what it does. But Gerald, what is an indicator? What is it composed of?
An indicator gives an indication of the presence of a particular substance which you're testing for.
Good. So that's again a characteristic, right? It's like we're describing humans can read and write literature, but I'm asking you, what is a human composed out of in terms of chemistry? In the same way, what is an indicator made out of? Priyasat?
Are indicators mostly acids?
Yeah, so indicators are mostly weak acids. Now, this term about weak and strong for an acid is everything to do with degree of ionization. So if an acid reacts to completion, aka it's going to release all its hydrogen ions, we call that a strong acid. So an example would be, let's say, HA. If it completely released all its hydrogen ions, an A-, we'd say that is a strong acid because the degree of ionization or forming ions is 100%. Does everyone agree? But if we had equilibrium errors, what can you tell me about degree of ionization? Is it greater or less than 100%? Obviously less, right? You can't be more than 100. But what would that make this acid? Is it now a strong acid or a weak acid?
Weak.
Good. So strong or weak is everything to do with degree of ionization. So we've got a weak acid here. We know it's weak because it's forming equilibrium errors. Now, whose principle must it obey?
Chatelains.
Exactly, right? So that's the first feature of most indicators. Most of them are weak acids. There are some cases where they're weak bases, but we'll focus on the case where they're weak acids. The second feature of indicators is that this ion here, we're going to call this the H. I'm going to replace A with Ind. So Ind is just going to be the anion that's bound to the hydrogen. Okay, so in this case, it's going to be Ind minus. So it's an indicator we're talking about. Now, let's imagine that, say this is yellow. The H-Ind ion will absorb all wavelengths and reflect yellow light into your eye. So you see it as a yellow solution. Whereas the Ind minus ion is a blue color. That's Ind minus, a blue color. So what would the solution be at rest when there's comparable amounts of H-Ind and Ind minus? What color would we see?
Yellow.
You sure? What happens when you mix blue and yellow?
Green.
Oh, green.
Yeah, we get a green color, right? So year 7 art, you mix yellow and blue, you get green, right? You apply that again in chem. They actually asked this in a trial paper, which is very weird. But coming back to this, yeah. So this will give you a green color at rest, okay? So now I want you to imagine that we get a drop of this green indicator and we add it to a solution full of hydrogen ions. It's an acid. Give you all about 20 seconds to think about this. What color would the indicator turn in this acidic solution, and why? Who's got an answer? Take it away.
Well, if putting the indicator into that solution, that would increase the concentration of hydrogen ions. So according to the Chatelain's principle, the reverse would be favored to decrease the concentration of hydrogen ions, and thus the solution, the indicator will be more yellow.
Good. It will shift to the left-hand side and thus become more yellow. Very good. Good. So do you see how this indicator has changed color in an acidic solution, doing exactly what an indicator does? Now, what about, Gerald, if we had a solution that was basic? We've said that basic solutions have hydroxide ions in aqueous solution. So again, what would be the steps here?
So wait, is it the same indicator?
Yep, exact same indicator.
Okay.
Solution.
Well, when you add the indicator into a solution, they neutralize. So you would have a decrease in hydrogen ions.
Good.
And the opposite would be to increase hydrogen ions.
Good. So you mentioned that hydroxide ions in solution will neutralize the hydrogen ions in this indicator, and thus the equilibrium will shift to the
It shifts to the
right
right.
hand side. Good. And since we're shifting to the right-hand side, we become
Blue.
blue. Exactly. So do you see how this indicator is now differentiated between an acid and a base? That is how indicators work. So if you ever asked how an indicator works, you need to bring up this equation that it's a weak acid. You need to also bring up that there is a distinct color for H end and end minus, and then explain in terms of LCP color change in an acidic and basic solution. Do we now understand how an indicator works? Any questions? Good. All right, so now what I'm going to do is we're going to pause mod 6. There's a question I just reminded myself of that I wanted to give you. I guess this question is quite good to try. Okay, here's your question. It's mod 5. The question is from the Balcom Hills 2021 HSC trial paper. So what I'd like you to do is spend a minute, and when you've got an answer, raise your hand, okay? And I'll pick on one of us to break it down for me. Okay, so Risat, what's your answer? A, B, C, or D?
I've put D.
D? Okay. And Gerald, what's your answer?
I got B.
Okay. Risat, why did you pick D? Tell me your thought process.
Okay. I put. Sorry. Okay. I put D because first we know that 60 grams. It's 60 grams of calcium carbonate in 1 liter. So we know that 1 liter evacuated container. So that means the number of moles that is in the calcium. Based off the stoichiometry, we can see that the same number of moles of carbon dioxide is produced from calcium carbonate, or I mean, not the same, but same amount for calcium oxide and carbon dioxide. So when I looked at for 120 grams, I thought that double the amount of moles would be produced in the same 1 liter evacuated container. So I thought the answer would be D.
Okay.
That would be double
You'll
the
be
production.
completely right if you saw this. Right? If it was a unidirectional arrow, then you can actually say that, okay, well, all of this gets converted to this, so I can apply stoichiometric ratio to find this, and I can use stoichiometric ratio to find this, right? But with an equilibrium, you don't know where the equilibrium position lies. What if it lied very much to the left, where only, let's say, 1 out of a million molecules of CaCO3 actually converted into this product, and thus the concentration of these two are very low. It's very high for this. We're not sure what that is, and I guess the next thing we have to consider is you always have to ask yourself these 3 questions. The second you deviate from that is when you start making mistakes. Gerald, what's the stimulus, if any?
An increase in the calcium carbonate concentration.
Is there an increase in the calcium carbonate concentration, Gerald?
Well, there's more calcium carbonate, but there's no change in concentration, really.
No stimulus. So is there any opposite or direction?
No.
No. So what would you expect your answer to be? The exact same as it always was. All of this is just to bamboozle you, right? This is all just random numbers they're throwing around to see if you can filter out the noise and focus on the signal. The key point here is calcium carbonate is a solid. You need to draw this out so you understand this, right? If you have 2 containers, one with 60 grams, one with 120 grams, as you can see, there's more moles in the second container, but the volume would have also increased in proportion to maintain a fixed concentration. When you're talking about a solid, the volume is not the volume of the container, it's the volume of the solid. Do we all agree? It's only gases which will occupy the entire volume of the container. And that's why when we change volume of a container, for example, with a gas, that's going to affect concentration. But for a solid, it doesn't affect anything. The key principle here is solids have a constant concentration and thus are not included in the K constant, and they do not affect Le Chatelier's principle. Does that make sense? Good. Good job. All right. And I guess the final question I wanted us to quickly have a look at is question... You can do this in your own time. Do you both mind screenshotting this? This is question 23, 23 B and C. But I'd like you to focus on C. So take a picture of this for me. Good. Are we both taking a snapshot? Okay, you can do this in your own time. And question I wanted you to do was this question. Question B. Good about A. You can do A. I think doing A would be good, but A and B. So what I'm going to do now is again give you about 2 minutes or so. Can you raise your hand once you've done A and B? So do A as fast as you can, but focus on B. I don't care about you writing. Once you've got an answer in your head, you can articulate to me, raise your hand, okay? Okay, Gerald, so is the reaction endo or exothermic?
It's exothermic.
Very good. And I guess you can apply the same 3 questions to get that answer, right? As temperature increases, the yield of product decreases, which means we have favored the reverse reaction in an attempt to decrease temperature. So if the reverse is endothermic, the forward is exo. Good. Next, what about B, Riyasad? What's your answer to B? Why are we still using high temperatures when high temperatures decrease yield of the very substance we are trying to industrially produce?
Okay, so yeah, I haven't written my answer, but I'm just I think I know how to explain it. Say well, increasing the temperature increases the kinetic energy of all I guess particles in the system in the reaction, and that increases the rate of collisions and therefore the number of successful collisions, which increases the reaction rate. So as a result, there will be an increase that there is a moderately high temperature is used to form more methanol quickly, much quicker than just So
Good.
yeah.
I like that explanation. The only one thing I was looking for was you need to mention this buzzword. And I love hearing this buzzword. We are achieving a compromise between rate and yield. This is a very important problem in chemistry. When you'll notice this is for exothermic reactions, in particular, exothermic equilibriums, that a high temperature equals fast rate, but it will always equal to low yield. So with any exothermic equilibrium, we reach this conundrum where we have to balance out and find the one temperature in which we make fast enough product in sufficient enough quantity. Okay, so if I were to give a headline answer for this question, it would be high temperatures are used to achieve a sufficient yield of methanol at an adequate rate. And then you can explain the compromise between rate and yield can be explained and then go on to collision theory.